Hello everyone, I am Barış Zöngür. We will present activation subspaces for out-of-distribution detection, a joint work with Robin Hesse and Stefan Roth in affiliation with TU Darmstadt. The task of out-of-distribution, in short OOD detection, refers to discriminating in-distribution inputs that belong to the training distribution and the OOD inputs that are outside of any class in the predefined class taxonomy. One line of research in OOD detection, activation shaping methods, prunes and scales the activation channels to produce activations that are easier to discriminate. On the other hand, distance-based methods utilize the position of activations in the embedding space under the assumption that the activations of in-distribution inputs should be closer to the training samples than those of OOD inputs. In practice, OOD inputs can also produce activations that lie close to the training samples, since models often bias activations toward aligning with a class vector in the linear classification hat to maximize the softmax output. However, directions unused during training and thus insignificant for the model's decision remain unaffected by this enforced alignment and can be useful for OOD detection. On the other hand, the insignificant directions can interfere with decision-related information on activations and distort the response of activation shaping methods. To identify the insignificant directions, we investigate the right singular vectors of the weight matrix in the linear classification hat, where W is the weight matrix, A is the activation vector, and L is the logits. When we apply SVD to the weight matrix W, the rows of V transpose form a basis for the activation space, and the singular values show how important each direction is for the output. From this, we define two subspaces. The decisive subspace V left spanned by the directions with high singular values that maximally affect the model's decision, and the insignificant subspace V right spanned by the directions with low singular values that have minimal effect. Accordingly, we denote A left the decisive and A right the insignificant component as components of the activation lying in each respective subspace. The insignificant component is unseen by the model during training, and because of this, the model behaves akin to a random neural network with respect to it. Such networks have been shown to produce powerful features, and we leverage this for OOD detection. We define the distance-based score function as right using the average cosine similarity to the nearest neighbors from the training data. We further propose that the insignificant component interferes channel-wise with the decisive component. To mitigate this, we apply activation shaping selectively to the decisive component and define the score function as left using the energy function calculated from the shaped activations. To combine the discriminative information from both subspaces, we merge the distance-based score function as right of the insignificant component with the activation shaping-based score function as left of the decisive component via product. This gives our final score function as double arrow, which we called actsub. In this experiment, we use a ResNet 50 model trained with ImageNet 1K classes. For OOD, we use iNaturalist, sun, places, and textures datasets. We report the false positive rate when the true positive rate is at 95%. A lower score indicates better results. We observe that with the complementary effect of both subspaces, our method actsub outperforms the closest baselines in all four datasets and achieves state-of-the-art results on average. In this work, we define two orthogonal subspaces of the activation space, insignificant and decisive, which contributes minimally and maximally to the classifier output. We observed that the insignificant component, untainted by the classification task, yields powerful features akin to a random neural network, which is discriminative for OOD detection. We further identify and mitigate the channel-wise interference on activations by selectively applying activation shaping to the decisive component. We combine the discriminative information from both subspaces and define our final score actsub. With the complementary effect of the subspaces, actsub achieves state-of-the-art results. Thanks for listening. Please refer to our paper for more details and further analysis.